Scientists just watched a machine in the Chilean mountains light up 800,000 times in a single night, and almost nobody outside the astronomy world noticed. That number is not a typo. In one night, one telescope flagged 800,000 separate changes in the sky, and it did it in under 2 minutes each time. Stick with me, because by the end of this video, that number is going to look small compared to what this same instrument is about to do next. And if you want to catch every update the moment this telescope makes headlines again, go ahead and subscribe right now before we get into it. The telescope we are talking about is the Vera C. Rubin Observatory, sitting on a mountain ridge called Cerro Pachón in northern Chile, more than 8,000 feet above sea level. This is not a brand new name. Astronomers have been building toward this moment for close to 2 decades, and the observatory first opened its eyes to the public back in the summer of 2025 with a set of test images that already stunned the scientific community. But what happened earlier this year is a completely different milestone, and it is the reason people are calling this the true beginning of the telescope's real career. On the night of February 24th, 2026, Rubin switched on something astronomers had been waiting years for, a live alert system. Instead of just quietly gathering pictures for scientists to sort through later, the observatory started comparing every new image against everything it had already photographed before, spotting anything that had moved, brightened, dimmed, or simply appeared out of nowhere. The moment it noticed a difference, it fired off an alert to researchers around the world, and it did this within about 2 minutes of actually taking the picture. On that very first night, it sent out 800,000 of these alerts. New asteroids drifting through our solar system. Stars suddenly exploding as supernovae. Distant galaxies flickering as matter spirals into the supermassive black holes at their centers. Variable stars pulsing in ways that had never been logged before. All of it flagged, packaged, and delivered to scientists' computers before most of us had even finished breakfast. Here's the part that makes this genuinely hard to wrap your head around. 800,000 alerts in one night was just the opening test. The people running this project expect the number to eventually climb to around 7 million alerts every single night once the telescope is running its full survey. Over the full 10 years this observatory is scheduled to operate, scientists are projecting something like 20 billion individual alerts in total. 20 billion moments of the universe changing, each one caught, logged, and shared with researchers almost as it happens. To put that in perspective, most of human history's astronomy has been built on catching a tiny fraction of these events, usually, well after they already happened, usually by luck, usually because somebody just happened to be looking at the right patch of sky at the right moment. This telescope is turning that entire process upside down. So how does a single instrument actually manage to notice 800,000 changes in one night without a small army of humans staring at monitors around the clock? The answer comes down to a method astronomers call difference imaging, and honestly, it is one of the more elegant tricks in modern observational science. Every time the telescope points at a patch of sky, its software pulls up a reference picture, essentially a composite built from every previous image the observatory has ever taken of that exact same patch, blended together into one clean baseline. Then it takes the brand new image and subtracts that baseline from it pixel by pixel. Anything that hasn't changed cancels out almost perfectly. What's left over is only the differences. A dot that wasn't there yesterday, a star that used to be dim and is suddenly blazing, a smear moving in a way that doesn't match any known object. That leftover signal is what triggers an alert. It is a bit like taking 2 nearly identical photographs of the same room a day apart and instantly highlighting only the objects that moved, without needing to manually compare a single item yourself. Making that work at the scale Rubin operates at required a genuinely enormous engineering effort behind the scenes. On a normal night, this observatory is capturing somewhere around 10 terabytes of raw image data. All of that has to be processed, calibrated, compared against historical reference images, and scanned for anything unusual. And it all has to happen inside a window of just a couple of minutes per exposure, night after night, without a single human being in the loop slowing things down. The team that built this pipeline has spent years refining the algorithms, the databases, and the sheer computing infrastructure required to pull it off, and getting it working reliably enough to launch publicly this year is being treated as one of the last major milestones before the observatory's flagship 10-year survey formally begins. And that survey, once it kicks into gear later this year, is really where the story gets even bigger. This isn't a telescope built to zoom in tightly on one object and study it in painstaking detail the way many of the most famous space telescopes do. It is built to do almost the opposite, sweeping across enormous sections of the sky, night after night, for an entire decade, essentially assembling a continuously updating movie of the whole visible universe rather than a single photograph. Astronomers involved in the project have said that in just its first year of full operation, This one instrument is expected to capture images of more individual objects than every other optical observatory in history combined. Not more than most, more than all of them added together. A huge part of what makes that possible is the hardware itself. At the heart of the observatory sits an 8.4-meter mirror paired with the largest digital camera ever built for astronomy. A machine roughly the size of a small car, capable of capturing over 3 billion pixels in a single exposure. Behind that camera sits a purpose-built processing system engineered specifically to keep up with the flood of information a camera like that produces every single night. It is less like a traditional telescope and more like a factory built to manufacture discoveries on an industrial scale, except the raw material rolling in is starlight instead of steel. The camera itself deserves a moment of its own attention, because it isn't simply a scaled-up version of an ordinary sensor. Inside it sits an array of individual detectors, each one carefully calibrated, so that when all the separate segments are stitched together, the final picture reads as one seamless image rather than a visible patchwork. In front of those detectors sit a set of enormous precision ground lenses, engineered specifically to correct for distortion across a field of view far wider than almost anything used in astronomy before. Without that correction, an object sitting near the edge of the frame would come out smeared or warped compared to something sitting dead center, which would undermine the entire point of scanning such large sections of sky in a single shot. The camera can also cycle through different optical filters, letting it capture light across the ultraviolet, visible and near-infrared range in quick succession, each wavelength revealing something slightly different about whatever it happens to be looking at, from the temperature of a star to the chemical makeup of a distant cloud of gas. None of that complexity is really about producing a prettier picture. It exists so that every single exposure carries far more hidden scientific information than a photograph in the traditional sense ever could. Now, asteroids are probably the easiest part of this story for most people to get excited about, simply because they feel the most immediately relevant to life here on Earth. When Rubin ran its very first test observations back in the summer of 2025, in just over 10 hours of pointing at the sky, it identified more than 2,000 brand new asteroids nobody had ever cataloged before, including several classified as near-Earth objects. For comparison, all the world's asteroid tracking observatories combined typically log somewhere around 20,000 new asteroids across an entire year. This telescope matched a meaningful slice of that annual total in less than half a day of testing before its real mission had even begun. Now that the alert system is live and the full survey is coming online, researchers are projecting that Rubin could end up cataloging millions of new asteroids, comets, and other small solar system objects over its full 10-year run. That matters well beyond scientific curiosity. Every one of those objects that gets tracked early is one less unknown hanging out there in the dark, and a telescope capable of catching faint, fast-moving objects that older surveys would have simply missed gives scientists dramatically more lead time to study anything that might eventually warrant real concern. But asteroids are really just the most tangible piece of a much bigger scientific puzzle. One of the observatory's core missions is to catch transient events, meaning anything in the sky that flares up, fades, or otherwise changes on a timescale of minutes to days. Supernovae are the obvious headline grabber here, stars detonating in distant galaxies with enough force to briefly outshine every other star around them. Historically, catching one of these explosions early has depended heavily on luck, since a star might ignite and begin fading before any telescope happened to be pointed at that exact patch of sky. With Rubin's rapid, repeating scans and its new real-time alert system, astronomers are now being notified about these events within minutes of them actually happening, giving them the chance to point other instruments at the explosion while it is still unfolding, rather than studying the aftermath. The same goes for active galactic nuclei, the glowing cores of galaxies where supermassive black holes are actively feeding on surrounding material, flickering in ways that reveal clues about how these monsters grow over cosmic time. There's also a quieter, slower-moving piece of this mission that doesn't grab headlines the way asteroids and exploding stars do, but that scientists consider just as important in the long run. By tracking the positions, brightness, and subtle motion of billions of galaxies over the full decade of observing, researchers hope to build the most detailed map ever made of how matter is distributed across the universe. That map is central to one of the biggest open questions in modern physics, understanding dark matter and dark energy, the invisible forces that appear to make up the overwhelming majority of everything that exists, yet reveal themselves only through faint statistical patterns spread across enormous numbers of galaxies. No single image can capture that kind of pattern. It only becomes visible once you've measured the shapes, and distances of tens of millions, ideally billions of galaxies scattered across huge stretches of sky, which is exactly the kind of task this observatory was purpose-built to handle. Closer to home, scientists are also using this telescope to build out the most detailed map yet of our own Milky Way galaxy, largely by tracking a category of pulsing stars whose brightness rises and falls on a wonderfully predictable schedule. Because their behavior is so well understood, these stars function as reliable distance markers scattered throughout the galaxy, including in the faint, sparsely populated outer regions that have historically been almost impossible to study in detail. By tracking enough of them, researchers hope to trace out faint stellar streams left behind by smaller galaxies that collided with the Milky Way in the ancient past, essentially reading the scars of our galaxy's violent early history written into the positions of ancient stars most telescopes could never have picked out clearly enough to follow. And then there's the discovery that has astronomers the most openly excited, even though it hasn't happened yet. Every so often, an object drifts into our solar system that did not form here at all. Something that coalesced around an entirely different star, got flung out into interstellar space and happens to pass close. Enough to our sun for us to notice it before it continues on its way, never to return. Only a small handful of these interstellar visitors have ever been confirmed, and every single one was spotted somewhat by accident, often with only days or weeks of warning before it became too faint to study properly. Because Rubin scans such enormous stretches of sky on such a rapid, repeating schedule and now flags changes within minutes, through its live alert system, scientists genuinely believe the odds of catching the next interstellar visitor early, potentially months in advance rather than days, are higher than they have ever been. Each one of those objects would carry a kind of frozen chemical fingerprint from a completely different star system, offering researchers a genuine physical sample of material that formed somewhere else in the galaxy entirely, something no amount of theorizing from Earth could ever fully substitute for. All of this adds up to a genuinely strange moment in the history of astronomy. For most of the last several decades, the general assumption has been that the sharpest, most exciting discoveries come from telescopes launched into orbit or beyond, specifically to escape the blur and light pollution of Earth's own atmosphere. This observatory isn't trying to compete with that approach directly. It isn't built to zoom in with extraordinary precision on a single distant target, the way some of the most famous space telescopes are. Instead, it is proving that a well-positioned, well-engineered, ground-based instrument can do something. Space telescopes were never really designed to do it all. Watch the entire visible sky change in close to real time, night after night, for an entire decade. What is maybe most remarkable is that a meaningful chunk of this flood of information isn't staying locked away in university servers. Rubin's alert stream is already being distributed publicly through community platforms that anyone can access, meaning students, amateur astronomers, and simply curious people anywhere in the world can watch some of these changes get flagged in close to real time, right alongside professional researchers. Given how much data a single night of observing produces, having more curious eyes looking through it isn't just a nice gesture toward public science. It genuinely increases the odds that something unusual buried in that flood of alerts gets noticed and studied a little bit sooner. It's also worth pausing on just how different this approach is from the way astronomy has traditionally worked. For a long time, getting access to genuinely cutting-edge observational data meant belonging to a university, a research institution, or a well-funded lab with specialized training and expensive computing resources most individuals simply never had. By building public-facing tools around a data stream this large from the very start, the people behind this project are effectively lowering that barrier in a way that hasn't really been possible before at this scale. A hobbyist with a laptop and genuine curiosity can now, in principle, look at some of the same alerts landing on a professional astronomer's screen almost as they happen, rather than waiting years for a simplified summary to eventually make its way into a documentary or a textbook. Over the full 10-year survey, the total volume of data this observatory produces is expected to reach into the hundreds of petabytes, an amount so large that fully analyzing it will likely occupy research teams for years, possibly decades, long after the observing itself is wrapped up. That is precisely why opening the door to more people, not fewer, matters so much here. Nobody, not even the largest research institution in the world, can manually comb through that much information alone. So here's where all of this actually lands. In one night, back in February of 2026, a single telescope in the Chilean mountains fired off 800,000 alerts about a changing universe, each one delivered to scientists within about 2 minutes of the moment it happened. That number is expected to climb towards 7 million alerts every single night once the telescope's full 10-year survey gets underway later this year, adding up to something like 20 billion individual moments of cosmic change over the full mission. Somewhere inside that flood will be new asteroids worth tracking, stars exploding in real time, black holes flickering as they feed, ancient stars mapping out the hidden shape of our own galaxy, and quite possibly, if researchers get a bit lucky, the next confirmed visitor from another star system, entirely caught early enough this time to actually study properly before it disappears back into the dark. Astronomy has spent most of its history working in snapshots, one object, one observation at a time. What this observatory is building is something closer to a live, continuously updating record of the entire sky, and we are still only a few months into watching it switch on. If you want to keep following along as this telescope keeps making headlines, from new asteroids to potential interstellar visitors to whatever it catches happening live next, make sure you're subscribed with notifications turned on, drop a comment with which part of this surprised you the most, and share this with anyone you know who would genuinely appreciate just how much one telescope on top of a mountain in Chile is quietly rewriting how we watch the universe.